We have come to the last video or collection of videos for the course, and they will cover Chapter 8, so 8.1 Interpretations and 8.2 Soundness in Predicate Logic. So we're looking at semantics now in predicate logic, or applying some meaning to really interpret the well-formed formulas that we have developed in this logic. So the learning outcomes for this section are to first give examples of partial interpretations of first-order formulae. So we'll define what interpretations are and give examples of interpretations of first-order formulae. And then we're going to use these interpretations to determine whether a schema is universally valid or a derived rule of our logic, giving a proof if it is, and if not, justifying with a concrete interpretation or a countermodel, or by proving the invalid strong generalization. So basically, the new part is generating these countermodels to justify why a particular schema or well-formed formula in our logic is not universally valid, or essentially not true, or not an absolute theorem or derived rule of our logic. Okay, so we're going to begin by determining or defining what we mean by an interpretation. So an interpretation is a pair denoted by a script D. We use D because that stands for the domain of this particular interpretation. So we fix a pair D and M, which translates a particular formula into its interpretation with respect to this pair. So the D corresponds to the domain that we're looking in. So we're looking at the particular language within mathematics. So in particular, oftentimes we will use a set of numbers like the natural numbers, or a particular finite set of numbers, a set of real numbers, the integers, whichever domain you wish to choose. And then we need to also define a translator M, or a mapping, which maps each element within our predicate logic to an element either within our domain or a truth value to give a truth value to the statement we're translating. So essentially, the interpretation allows us to interpret the meaning or the semantic meaning of the particular well-formed formula. So let's look at how this translator map is defined in general. So we apply the translator M to various elements of our logic, or alphabets, members of our alphabet in our logic, so top, bottom, Boolean variables, object constants, functions, and predicates. So all of these are the new elements we've added. So to the Boolean objects, the old ones that we have, we're going to give them the typical true-false values that we had before. So top, for example, is always true in any interpretation, and bottom is always false in any interpretation. Any Boolean variable can be either true or false, just like before. Now we want to translate and give meaning to all of our new members of our alphabet. So every object variable simply becomes a member of the domain. So as we mentioned before, these new elements in our alphabet are meant to provide additional meaning to our statements. So depending on the language we're talking about or the domain of mathematics we're talking about, these object variables stand for the objects within that domain. Similarly, the constants also stand for members in that domain. We define the functions to be specific functions applicable to objects in D. So these are functions defined from elements in D to elements in D. And the predicates are predicates or relations applicable to objects in D. So these define relationships between objects in D as well. And finally, everything else remains unchanged. So all of the connectives, the brackets, the equal sign, all remain unchanged by the map. But we know what their meaning is based on how we've defined them before. Okay, so that simply introduces what we're going to cover in this section, as well as what an interpretation is. And the next video will explore how to use interpretations to translate well-formed formulae into their applicable interpretations.